Hi, what's on the workbench today is something special. It's a UTS3060A signal analyzer from UNI-T. It's from the UTS3000A series, and this specific model can analyze signals from 9 kHz all the way up to 6 GHz. Thanks UNI-T for loaning me this unit, so I can show you what it is capable of. And by the way, I realize that there's glare in the background. I think once I power it on a little bit later, the situation should improve. Anyway, this is a rather expensive piece of equipment. The UTS3060A retails for around $8,500 at the time of filming this video. It's not something a typical hobbyist would be able to afford, but hopefully through this video you can get a sense of what to expect from a modern signal analyzer. At the center of this UTS3060A is a spectral analyzer with a tracking generator. You can see the tracking generator input. And the reason it is called a signal analyzer rather than a spectral analyzer is because, besides being able to measure the magnitude of the signals, this analyzer is also capable of measuring the phase information of the signal. In fact, with options enabled, this signal analyzer can perform IQ signal analysis, EMI measurements, analog demodulation, vector signal analysis, real-time spectral analysis, and it even has a full-fledged 2-port VNA or vector network analyzer built in. With all these capabilities, clearly I can't possibly cover everything in a single video. So in this episode, I'm going to concentrate on the spectral analyzer portion of this UTS3060A, along with a few other relevant features. And in a future video, I will be covering some of the other functionalities. So be sure to stay tuned. Now, maybe I'll spread out the content a little bit so you don't get tired of me talking about the same device all the time. Also, I'm not going to bore you with each individual settings as those are highly specific to different devices, and there's a manual for that. And the user manual is actually quite comprehensive, and it has 90-odd pages. So what I'm planning to do is to demonstrate the capabilities of this signal analyzer through some examples and some experiments. Alright, I just plugged in the power, and let's actually power it up. Now, just like a lot of the modern test equipment, it does take quite a bit of time to boot up. While we're waiting for it to boot up, you probably have noticed that the dimension and the overall design of the UTS3060A look very similar to those of the latest UNI-T MSO3000X series oscilloscopes. It features this 10.1-inch touchscreen display, and the display has this oleophobic coating, which is very smooth to the touch. I guess we'll have to wait a little bit longer. Alright, now it has booted up. The first thing you'll notice is just how fast the sweep is. Of course, the speed of the sweep is dependent on the bandwidth we're looking at here and also the resolution bandwidth. Currently, it's sweeping the entire frequency band up to 6 GHz and the resolution bandwidth is 10 MHz. And this is the power on default mode, I think. Now, you can select whether to boot into the default mode or your last worked on configuration. Because there's just so many settings, you can easily forget what you had set before. So my preference is to boot into a default known state so that I know exactly which parameters I need to change to set up my test. And also conveniently, here you have a default button and you can just press it. It will reset everything to the factory default if you forget where you are. You can use gestures to control the range and move the spectrum around, just like how you would interact with a tablet. Now, of course, you can also control the user interface with the control buttons on the right-hand side here. And you can even hook up a keyboard and a mouse and use them to control the user interface if you want to. The UTS3000A series has 3 USB ports here in the front, which makes it very convenient if you want to hook up other devices. So let me just quickly show you the user interface here. For example, if you don't want a sidebar, you can actually zoom in to the full screen. And here we have the sidebar, and you can set the center frequency here. So let's say we want to set at 1 GHz. And we want a frequency span, let's say 100 kHz. And you can do it that way. And of course, you can move the spectrum up and down and left and right. So it's very, very intuitive here. So first, let me actually put in a highly pure sinusoidal waveform from my HP 8642B RF signal generator. Let me actually generate the signal, let's say 1 GHz. And let's do an amplitude of -10 dBm. And let's enable that. Of course, we can use the auto tune. Let's actually check that to see if we can capture the signal. Yep, and you can see that we captured the signal. It's -10 dBm. Because we have this relatively short cable, so the additional attenuation is actually minimum. The output currently set as -10 dBm. And the center frequency here, you can see, is right at 1 GHz. And right now you notice we have a resolution bandwidth of 1 MHz, so let's actually zoom in a little bit more. So let's do the frequency span. Let's say we wanted this to be actually 10 MHz. And you notice that the resolution bandwidth actually is currently automatically adjusted down to 100 kHz. Of course, we can actually tighten up the resolution bandwidth quite a bit. So let's first reduce the resolution bandwidth. Let's change it to, let's say, 1 kHz. Of course, right now you can see the sweep speed is a lot slower. Another thing you probably notice is that the noise floor dropped quite a bit after we reduced the resolution bandwidth. Let's actually reduce the frequency span here. Let's say we want to do 1 MHz. Of course, the center frequency is a little bit off because the clocks of these two devices are not in sync. So let's put it in the middle here. Now, for folks who are familiar with spectral analyzers, you probably know this already. But I do want to point out the differences of resolution bandwidth, the RBW, and also the video bandwidth. You can see here, that's VBW. You see that the resolution bandwidth determines our measurement frequency resolution. The narrower the resolution bandwidth, the more spectral details you can see in the captured spectrum. Also, the narrower the resolution bandwidth, the lower the noise floor, as we have shown earlier. For example, right now, we're at 1 kHz. You can see the noise floor is about 80 decibels down. And if I further reduce the bandwidth, let's see, for example, let's go to here. And if I do 100 Hertz, you can see that the noise floor moved down even further. And for our purpose, we wanted to scan faster, so let's go back here. Let's go to 1 kHz again. And by the way, the marker seems to be off now, so let's actually get the marker back on the peak here. So to do that, I think I need to press a marker, and let's try to figure out here. So let's do marker, and we wanted to search peak. Now you can see that marker is back onto this frequency peak at 1 GHz. In a traditional heterodyne spectral analyzer like my HP8566B back there, the resolution bandwidth filter is essentially the final stage IF filter before the detector, as you can see in this diagram here. Now, modern DSP-based analyzers like the UTS3000A, the filtering is probably done digitally, but the idea is pretty much the same. The video bandwidth filter, on the other hand, happens after the detector stage, and it's a low-pass filter that smooths out the display trace. Typically, the video bandwidth is set to be equal or lower than the resolution bandwidth. And now you can see here, we set at 1 kHz, which equals the resolution bandwidth of 1 kHz. So now let's actually reduce the video bandwidth and see what we get on the spectrum here. So we come here, and let's set it to, let's say, 100 Hertz. And you can see that essentially it filtered out most of the noise on the spectrum here. Of course, the update rate also slowed down. By the way, you have to set the resolution bandwidth low enough to be able to resolve the frequency components of your signal. If that is not set up correctly, no amount of video bandwidth filtering would be able to resolve the signal. As I just mentioned earlier, the speed of the sweep is impacted by either the resolution bandwidth or video bandwidth. By lowering either of these, you are slowing down the sweep speed. So typically what you wanted to do is first identify where the signal is on the frequency spectrum and narrow down the frequency range. And then you can reduce the resolution bandwidth so that you can observe all the frequency components you would otherwise not be able to discern with higher resolution bandwidth. Of course, you can also reduce the video bandwidth to further reduce the noise on the spectrum, as I showed you here. Let's further reduce the resolution bandwidth and let's see what the minimum we get on this UTS3060A. Let's actually change the frequency range here. So let's do the span. Let's change it down to, let's say, 10 kHz. Of course, we're not seeing the signal anymore, and you can see that we actually have this arrow here telling you that the peak is out of the range. So let's see if we can move it back. Yeah, this is our frequency range, and we'll worry about the peak a little bit later. Obviously, right now, we have to further narrow down the resolution bandwidth here. So let's change the resolution bandwidth to, let's say, 10 Hertz. And again, we get our very sharp frequency peak here. Let's change the video bandwidth to auto. So we'll change down to 10 Hertz. And we can further reduce the resolution bandwidth as well. So to do that, let's actually change the frequency span to 1 kHz. So let's take a look where the peak is. And let's change it down to, let's say, 1 Hz. And I think that's the lowest you can get. So of course, with a resolution bandwidth of just 1 Hz, you can see that the sweep speed is extremely slow here, but you do get very high frequency resolution on the screen. I just readjusted the setup. Right now the center frequency is at 1 GHz, span of 100 MHz with a resolution bandwidth of 1 MHz. What I'm going to show you next is how to observe a very weak signal. So right now the output of course is at -10 dBm. There's no problem showing the signal on the screen here. Now let me actually adjust the output amplitude down. Let's say we wanted the amplitude to be -100 dBm. And you notice that of course we can't see that signal anymore, but we know we're actually inputting a 1 GHz -100 dBm signal here. So how do we observe that? So as I mentioned earlier, the narrower the resolution bandwidth, the higher the resolution. So to do that, of course, we need to narrow down the resolution bandwidth, but let's actually change the frequency span to, again, let's say 1 MHz. Let's see if we can do that with this setting here. Yeah, you can kind of see the signal here, but if I change the resolution bandwidth, let's come here to, let's say, 1 kHz. Now you can actually see the signal right there, because right now the noise level had dropped significantly. You can see is actually -118 roughly dBm. So let me further reduce the amplitude to -120 dBm. Again, right now the signal disappeared in the noise. So let's actually see if we can get the signal back. So to do that, of course, we can actually change the video bandwidth. Let's see, we change the video bandwidth to 100 Hz. And remember, that will average out the noise. And of course, right now, we still don't see the signal. Let's further reduce the bandwidth here. Let's say we want to reduce the bandwidth to 100 Hz. And we further reduce the video bandwidth to 10 Hz. Let's see if we can see the signal here. And you probably see this is the signal that we're currently outputting from the HB8642B. That's at 1 GHz. So far, we just used the resolution bandwidth and the video bandwidth to clean up the trace. Of course, you can make the trace even more smooth by changing the trace type. So let's come here. By the way, we have 6 traces you can actually manipulate. We'll show you probably in some other videos, but right now you can see here, we have this trace and the detector type is normal. So if I make it, let's say, peak detection, and you can see immediately the noise level dropped, and that's because, well, the noise dropped, not the noise level, because we're essentially detecting the peak, and the peak becomes more prominent. So to observe these kind of weak signals, it's important to set up your resolution bandwidth and video bandwidth, and also the detector type correctly. Now I just changed the screen settings back, and I'm using the normal detection mode. Of course, you can use your hand gestures to change the display here. For example, if I want to expand the display, I can simply just use my fingers like this. That's to zoom in further. Of course, I want to zoom out. I can do this. So it's indeed very convenient to use. The UTS3060A also has preamp built in. Currently, the preamp is off. And let's actually now enable the preamp and see what effect it has on the signal here. Remember, right now we're inputting a -120 dBm signal, which is very weak. So let's actually come here and let's turn on the preamp. And you can see the effect of the preamp essentially is drop down the noise floor by about 20 dBm here. Now the signal is more prominent. Okay, I just reset the spectrum analyzer and let's move on to the next test. And by the way, as I mentioned, there are a lot of features of this UTS3060A signal analyzer that I wanted to show you, but it's not possible for me to fit all the content in a single video. So what I'm going to do is try to group similar topics together and cover them in a few different videos. I think I should be able to keep this signal analyzer till at least the end of April. So if there are any specific topics, use cases you'd like to see, please leave a comment in the comment section below, and I will try to show you guys if there is enough interest. Anyway, I thought what I will show you next is how to use the UTS3060A to perform face noise measurement, as this is something many of you would probably be interested in. So I just turned on the output from my HP8642B, and that's a 1 GHz signal at -10 dBm. So let me set up the spectrum analyzer first. So let me go to the center. So 1 GHz. And let's actually set the frequency span to 10 MHz. So I can see it better. And let's reduce the resolution bandwidth. Let's do 10 kilohertz. I deliberately set the frequency span a little bit higher at 10 megahertz as I wanted to show you the phase noise. And here you can see the skirt of this 1 gigahertz tone, and that is actually the phase noise in frequency domain. For an RF generator, obviously the lower the phase noise, the better the signal quality. Now, phase noise is essentially caused by the fluctuation of frequency, which can be caused by multiple reasons. For example, for a simple crystal oscillator, the phase noise can be partially due to the mechanics of the crystal, the thermal noise in the supporting electronics, and so on and so forth. Of course, for a complex RF generator like this, the source of this phase noise can come from many different sources, for example, from the VCO frequency divider, and of course, from the PLL as well. Anyway, so in real world, there's always going to be phase noise, but for a good quality RF generator, the phase noise is typically very low. There are a few methods for measuring phase noise, and one of the easiest methods is the so-called direct spectral method, which we can do with the spectral analyzer. So let's actually try to measure the phase noise of this 1 GHz signal from the HP8642B. But before I do that, let me actually further reduce the frequency span and resolution bandwidth. So let's change the frequency span, let's say, to 100 kilohertz. And of course, now we need to reduce the resolution bandwidth to 100 hertz. Now I have reduced the frequency span to 100 kilohertz and set the resolution bandwidth to 100 hertz. The unit of phase noise is dBc per hertz. It's essentially the noise power normalized to a 1 hertz bandwidth and minus the power of the carrier signal. Now, of course, right now the spectrum is a little bit noisy. To improve the measurement accuracy, let's actually turn on the averaging of the trace. Before I do that though, let's actually try to find the peak signal here. So let me turn on marker, and let's go to marker, peak. And you can see right now we are roughly at 1 gigahertz, give or take. And the current amplitude is -10 dBm, a little bit lower than that because of the cable loss here. So to turn on the trace averaging, let's actually come down here. So let's go to the trace. You can see here, we are actually doing clear and right. So let's turn on average. And also for the detector, I think we can turn on average as well. And now you can see this is our signal. I'm going to let it run for a while so that the trace will be cleaned up. So next, I'm going to enable the delta marker. So let's go to marker and let's see marker mode. Let's change it to delta. And here we have this delta frequency. And let me change it to 20 kilohertz. By the way, phase noise is typically specified at a specific offset of the main frequency. Sometimes it's 10 kilohertz, sometimes it's 20 kilohertz. You will need to refer to the specifications for the exact measurement that the manufacturer did when they specified the phase noise. Anyway, here I'm using 20 kilohertz. So immediately you can see that the delta marker measures the relative power to the main peak here. So the amplitude of the delta marker here is at -79.44 decibels. Of course, this number is not normalized. So for us to actually measure the phase noise, let's come to the function. And you can see band function currently is off. Let's change the band function to marker noise. And here we have a band span. That's 5 kilohertz. Let's leave it as is for the time being. I'll explain a little bit later. Essentially, what that band span is actually here. You can see we have this range. And essentially, it uses the spectrum within the band to calculate the normalized noise. In our case, it doesn't really matter that much, and I will show you a little bit later, as our noise floor here is relatively flat. You can see the calculated dB per hertz number here, -97.28. And in this case, because we're using a delta cursor here, essentially this is comparing between these two markers, which in this case is the normalized noise level relative to the carrier. So this number essentially is the dBc per hertz, and that's actually the phase noise. And this number is automatically calculated for us, so it's very convenient. Of course, you can always do the calculation yourself. To normalize the noise power to 1 hertz, you can take the logarithm of the resolution bandwidth and multiply it by 10. And in our case, this would be 10 times log 100 because we have this resolution bandwidth of 100. Essentially, if you do the calculation, you get the number of 20. And if you come back here, let's actually remove this calculation. So let's, for example, turn this off. You can see if we subtract 20 to the minus 79, it's not exactly the number we got, right? So for example, right now, let's go back. Let's turn on this marker noise. The calculation is minus 97. If we use the minus 20, it's actually minus 99. So why are these two numbers different? Well, here's the tricky part. Because the filters involved, modern spectral analyzers would typically apply some correction factors when calculating the noise power. The simple calculation we just did actually did not include any correction factors. Nevertheless, the simple calculation we just did should give you an idea of the ballpark number of the phase noise, and it's not too far from the actual measurement. Remember, we have this bandspan of 5 kHz, and a moment ago I told you that it actually would impact how the phase noise is measured. So let's actually take a look at that. So right now, remember, this number is 5 kHz. So let's go back here, and let's change the bandspan, say to 10 kHz. Remember the number here. So you can see we actually have a slightly different number. I'm not sure if you remember what the number was before, but let's change it again. So right now it's minus 97.4, and we come back here, we change this, let's say, to 20 kilohertz. You can see that because we have a relatively flat noise floor, so the actual measured number didn't change much. So let's restore it back to 5 kilohertz, and I'll show you again. You can see that essentially we're getting pretty much the same noise reading. Now, if you look at the specs for the HP8642B signal generator, you will see that the phase noise at 1 GHz with a 20 kHz offset is specified at minus 134 dBc per hertz. And what we measure here is quite a bit higher than that. So why is that? Well, remember, the noise floor of the spectrum analyzer is actually dependent on the resolution bandwidth. And currently, we're at 100 hertz. Of course, we could try to reduce the resolution bandwidth even further, and that should give us slightly better reading, but the scan speed would be extremely slow. So I think the main limitation here is actually the phase noise of the spectrum analyzer itself. The spec of the phase noise of the UTS3060A is essentially between 100 to 110 dBc within our frequency span. So we're approaching the limit of the spectrum analyzer. All right, let's actually use another RF generator and let's do the phase noise measurement again. Right now, I'm generating a signal from my HP8671A. The output signal is at 6 GHz, which is the upper end of the frequency limit of this UTS3060A. So let me put that signal to the center here. So let me set the center frequency to 6 GHz, and frequency span is 20 MHz, that's fine, and the resolution bandwidth is 100 kHz. Just by looking at this spectrum visually, you can probably already see that the noise floor from the HP8671A is significantly higher than my HP8642B. Let me reduce the span a little bit. So let's change the span to, let's say, 500 kHz. And let's change the resolution bandwidth here to 100 Hz. Let's reduce the bandwidth even further. Let's come back here. Let's actually go to frequency. And let's do a span of 100 kHz. And let me turn on the trace averaging again. So I come to trace, averaging, and we can turn on the detector average. Again, we'll let it run for a few minutes. And now I'm going to put a relative marker on the frequency spectrum here. So put a marker, and we change the marker mode to delta. Again, let's put 20 kHz. So that is measuring the relative power at the frequency spectrum right here. So you can see compared to the main peak, it is roughly 67 decibels down. Of course, that's not normalized. Again, we can enable the noise marker. So let's go to function and marker noise. You can see the bandspan is 5 kHz. We don't need to worry about that. So this is our measured phase noise at minus 84.8 dBc per hertz. So from the measurement we just did, you can see the phase noise of the HP8671A is a lot higher than the HP8642B. So now we see how easy it is to measure phase noise with the UTS3000A series signal analyzer. I'll be showing you more features in the next video, but let me quickly show you what are the available options. Let's first take a look at the options available here. On this loaner, many of these options are actually enabled. So let's come here. You can see that we have the spectrum analyzer. Of course, that's the main concentration of this video. And you can see we have a bunch of options here. Then we have the IQ analyzer, we have the EMI, we can do compliance testing. We also have the analog demodulation capability, which I'm planning to take a look in the next video. Next, we have the vector signal analyzer, which supports QAM, PSK, FSK, and so on and so forth. We'll definitely take a look at that in a separate video as well. Then we have the real-time spectral analyzer option, which probably will take a look shortly. This signal analyzer also has a vector network analyzer module, which would definitely deserve its own video. And of course, it also supports wireless signal analysis. We don't have this option enabled here, but the LTE, TDD, these are for the wireless communication stuff. And also the NR, I believe it stands for new radio. That's for the 5G radio. Now, of course, these options are highly specialized. They're quite expensive. Some of these options actually cost more than the signal analyzer itself. We also have the advanced measurement module enabled, and this allows us to measure channel power, occupied bandwidth, third-order intermodulation, and we have many more power measurement options as well. Of course, this signal analyzer has a tracking generator built in. So if you don't have the VNA module, you can still use the tracking generator for filter and amplifier measurements. And finally, we also have this 40 MHz real-time signal analysis module. Let me actually quickly show you this module. So let's exit out this option here. To get to these options, all you need to do is click on the spectral analyzer showing up here. And you can see that here are all the different modes you can select. Of course, I'm going to concentrate on some of these in future videos, but right now you can see we're in the spectral analyzer mode, and I can come down here. You can see here is the real-time spectral analyzer, and I can enable that. This option has a maximum frequency span of 40 MHz. Right now, you're looking at a sweep signal generated by the UTG-2082X from 0 to 40 MHz. Anyway, as I have demonstrated so far, the UNI-T UTS3000A series is very capable. The 3060A we looked at in this video can analyze signals up to 6 GHz. The entry-level 3036A can analyze frequencies up to 3.6 GHz. And the top-of-the-line UTS3084A can go up all the way to 8.4 GHz. I'm planning on making a few more videos with this signal analyzer. If there's anything you want me to show you, please let me know in the comment section below. Alright, that's all for today. I hope you enjoyed the video. If you like the content, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. If you want to further support my work, please consider joining the channel and becoming a member. Thanks for watching, and I will see you next time.